In homework question number 10, we're given a volume of a known concentration of a buffering solution, and we know it's pKa, but we don't know its initial pH. That is what we're trying to calculate. What we are told is that a certain volume of HCl was added, and this changes the pH to this final pH. Now, an important issue here is that the volume is changing, because we start out with 100 milliliters and we'll end up with 106 milliliters roughly. So even though the Henderson-Hasselbalch equation is how we relate pH, pKa, and the ratio of the concentrations of the conjugate acid and the conjugate base, because the volume is changing from the beginning to the end of the process, we really have to deal with the stoichiometry of the reaction in which one equivalent of H plus from hydrochloric acid reacts with one equivalent of conjugate base to give one equivalent of conjugate acid irreversibly. So here I've given some steps of working backwards to go from the final pH to the initial pH. So first, let's use the information we're given to solve for the ratio of the conjugate acid and base using the Henderson-Hasselbalch equation shown above. The final pH is 5.7, the pKa is 6.3, and we are solving for this ratio here. So to solve for that, I'm just going to have 5.7 minus 6.3 equals log of A minus over HA. This is minus 0.6 equal to that. And I'm going to take both sides, raise them to the power of 10, which is the antilog for a base 10 log. And we get that this term on the left equals 0.251 with one significant figure, because pH values are logarithmic numbers, and with logarithmic numbers, the number in front of the decimal point is the characteristic, and the number after the decimal point is the mantissa, and only the mantissa contributes significant figures. Because logarithms give us orders of magnitude, the characteristic is not a significant figure in the same way that in scientific notation, this exponent is not a significant figure. The characteristic and the exponent in this case are equivalent. The value and the mantissa in this case are equivalent. This is where you get your significant figures. Now back to the problem. We now know that this ratio is 0.251. And again, I'm retaining a couple extra digits just to prevent rounding errors. Now 0.251 is the ratio of conjugate base to conjugate acid. But because the volume is changing, we need to be dealing with amounts, like I mentioned here. So what amount of buffering acid did we start with? So in the problem we see we have 100 milliliters of 0.1 molar, and I'm just going to give that as moles per liter, so we can see how liters cancel out. And that gives us 0.01 moles, which I like to think of as 10 millimoles. In biochemistry, we think of a lot of amounts in terms of millimoles or micromoles or nanomoles. So given that we know we started with 10 millimoles of this compound, and some of the conjugate base was converted to acid by a reaction, we're going to have to reverse that process and realize that some of the final acid we have was originally conjugate base by the relationship that the initial acid is equal to the amount of final acid minus the amount of added HCl, and the amount of initial base is equal to the amount of final base plus the amount of added HCl. But to get there, we have to find the amounts of final acid and base. Since we started with 10 millimoles of the weak acid buffering compound, and no weak acid is added or removed from the system, we will end with a total of 10 millimoles. We just have to figure out the distribution of how much is in the base form and how much is in its acidic form. So there are a few ways to do that. One way that I think of it is to think that the final amount of conjugate acid is equal to this starting amount, 10 millimoles, times whatever the percent of HA was in the final solution. And likewise, the final amount of conjugate base is equal to 10 millimoles times the percent of the final conjugate base. And how do we get those percents? There are many ways to do this. One way that I think about it is to think that the percent of HA final is going to be expressed by HA concentration over HA concentration plus A minus concentration. There are many algebraic treatments to get you to this answer. The simplest for me is to think about this expression here as 0.251 over 1. And when I do that, I can basically now say that, at least in relative terms, using arbitrary concentration units, the concentration of A minus is 0.251 of the concentration of HA. And so I can use these as equivalencies and plug them in over here, like so. 1 over 0.251 plus 1 equals 0.80. I can likewise express final percent of A minus as concentration of conjugate base over HA plus A minus, and that would be equal to 0.251 over 0.251 plus 1. And if I work that out, that's going to be 0.2 with 1 sig fig. And I'm carrying the 0 as a guard digit for rounding errors. Additionally, since this is a percent, you could also have just taken the percent of conjugate base is simply 1 minus 0.8. And that would have gotten you the same answer. So now we know these terms. We can now solve and find that the amount of HA final is equal to 10 millimoles times 80% or 0.8, and that equals 8 millimoles. And likewise, the final amount of conjugate base is 0.2 or 2 millimoles. So now let's move on to part 2 of the solution. Using this relationship, the amount of initial conjugate acid is the final conjugate acid we just calculated, 8 millimoles, minus the amount of HCl that was added. How much HCl was added? So we have 6 milliliters times 1 molar, and that works out to 0.006 moles, which is the same as 6 millimoles. So when we plug that value in here, we have 6 millimoles, or 2 millimoles. And to calculate the initial amount of conjugate base, we can either use this relationship here, or since we know the total is 10, we can just say 10 millimoles minus the 2 millimoles shown above, or 8 millimoles. So now we can set up the Henderson-Hasselbalch equation and calculate that the initial pH is simply the pKa, 6.3, plus the base 10 log of 8 millimoles over 100 milliliters on top. That's our concentration because our starting volume was 100, divided by 2 millimoles over 100 milliliters. Now note that all these, the volumes and these units actually cancel out. The most important thing is to know that the ratio of the initial solution was 8:2 base to acid. The ratio of the final solution after adding the HCl was 2:8 base to acid. So we just reversed that ratio in a sense, which is a coincidence, but that the numbers match, but it is what it is. And so if we plug the numbers in, we get 6.9 is our initial pH, and that is with 1 sig fig, because again, the characteristic is not significant, only the mantissa. And all throughout, we've been basically dealing with 1 sig fig, because our limiting precision has been the 6 milliliters, the 0.1 molar, and this pH and pKa value. And there you have it.